Hey Honors Chem Stars, it's Ms. Macaulay bringing you your Chapter 9 homework, page 8 and page 9. We're looking at mass to mass and volume to volume calculations using stoichiometry. Here's a new fun thing I learned. On the new Smart Notebook, if I click on this, it changes the color. Oh my gosh, so exciting. We're going to go with teal, why not? Let's look at problem 1. Problem 1 asks us to determine the mass of carbon dioxide, so they're asking for how many grams of CO2 can be produced when 0.85 grams of butane, that's like the type of hydrocarbon that's in little click lighters, reacts with oxygen. Now I'm already identifying that's excess. Are you going to run out of oxygen in the room? Probably not, so there's going to be more than enough oxygen, according to the following equation. So I'm just kind of color coding it here. So 2 butane plus 3 oxygen will yield 8 carbon dioxide plus 10 water molecules, or moles. Okay, so let's start identifying what we know. We know that before the reaction starts, we're going to have some number of moles of butane. We've got to come over here and figure out how that grams converts to moles. We know before the reaction starts, there's enough oxygen, and we know that before the reaction starts, there aren't any products. Then during the change, we're going to be using up all of that butane. We know that there'll be none left over. And we are going to use up a certain amount of oxygen, but we know there's going to be a lot. We'll use some, and there'll be a lot left over. And we know that we're going to be creating positive products, and they're asking for how many grams of CO2. So we're going to take those grams out of the BCA table, or the moles out of the BCA table, come over here and convert. Okay, so first things first, we've got to get moles into the BCA table. Only moles ever go in. So let's go do a little factor labeling problem on the side. 0.85 grams of butane equals how many moles? Well, I need to know the molar mass. And so where do I go for that? Your brain better be screaming periodic table to you. So let's go to the periodic table, C4H10. So we're looking for C4H10. Well, look at that. So carbon has a molar mass of 12.01. Hydrogen has a molar mass of 1.01. When we add up all those parts, the molar mass of C4H10 or butane is 58.14 grams per mole. So 58.14. So 58.14. Now to get my moles, we're going to use our calculator. And we're going to take 0.85, divide by 58.14. And there was 2 sig figs in the problem. Let's keep like 3 in our work. So it's going to be 0.0146. 0.0146. So this number comes in right here, 0.0146. That's my moles of butane, goes right here. So how much of that will be used up? All of it. We're going to use up 0.0146, and there'll be none left over. We're completely reacting it. Now they want to know about the mass of CO2 produced. So how much CO2 will be produced? Well, this is my limiting reactant. So we're going to use that mole value, the coefficient. So 0.0146 times the mole ratio from our balanced chemical equation. Remember, this up here is our recipe where we get the mole ratios from. So the mole ratio of our known butane and our unknown carbon dioxide ratio is 8/2. So we need to take 0.0146 times 8/2, that's times 4. So times 4. And let's take about, let's take 3 sig figs. We'll round here a little bit. So 0.0585. 0.0585. Now that's how many moles of my carbon dioxide I have, but the problem wants to know grams. Okay, so we're going to take this number right here. We're going to plug it in 0.0585 moles of carbon dioxide. We want to get rid of moles and go to grams. How did I get this number? Well, I went to my periodic table. Carbon dioxide, 1 times carbon's mass plus 2 of oxygen's mass gives me 44.01. So let's use our calculator. So 0.585 times 44.01. We're going to get a final answer of 2.573 grams. So 2.573 grams. Now look back at the original problem. There's 2 sig figs. So let's round to that 5. So it's actually going to be 2.6 grams of CO2 is my final rounded answer. I know that I kind of abbreviated my numbers when I put them in the table, but I did keep the whole values in my calculator. We want to try and only round at the very end. That limits the uncertainty in the problems. Okay, that was number 1. Let's keep going. Let's try number 2 next. Oops. Let's see here. So number 2. Number 2 says determine the volume of oxygen required in the above reaction to produce exactly 94.5 liters of carbon dioxide. Now, we've been going with the BCA table for all these problems in Chapter 9. I'm going to show you the old school way of doing it. It'll save us a little bit of time. You could totally do this problem using your BCA table, but I'm going to show you the longer factor labeling way. So let's kind of figure out each step. So determine the volume. This is unknown. So this is your unknown to produce 94.5 liters of CO2. This is your known right here. Okay, so we're going to start with that known, that 94.5 liters of CO2. Put that over 1, just like we always do. Now we want to get rid of liters of CO2, and you're always trying to go to moles. So we're going to divide by 22.4. And if we look, that cancels liters of CO2, and we're at moles of CO2. Now, how do we convert from moles of one substance to another? We go back up to that balanced chemical equation up here, and we find the mole ratios out of it. So that's where this number comes from. So what we're saying is that for every 8 moles of CO2, there are 13 moles of oxygen needed. And if you look really carefully, now you see that my moles of CO2 cancel, and I'm left with moles of oxygen. Okay, they want to know volume of oxygen. Well, once I've gotten moles of oxygen, it's super simple to go to the volume. I have to multiply by 22.4. So if you check all the units before we start, we're going to be left with liters of oxygen. Now all we need to do is pull up our calculator. Let's clear out our memory. So we've got 94.5 divide by 22.4. Okay. Now we need to do times 13 divide by 8. Now we're taking all the numerators, divide by all the denominators. So we got a 13 over 8 term. And now times 22.4. That's going to give us 153.5625. But how many sig figs do we want? We want 3. Okay, so 153.5625. And we want to round to 3 sig figs, because that's how many are in this part of the problem. 1, 2, 3. Look to the right, that'll round up. So it's going to be 154 liters of oxygen are necessary to produce that volume of carbon dioxide. Good. Let's go on to number 3. So here's a reaction. This is the elephant toothpaste reaction that you saw at the beginning of Chapter 8. Hydrogen peroxide decomposes into water and oxygen gas. What mass of hydrogen peroxide is required to, I'm adding the word exactly, produce 0.77 grams of water? Okay, so here's my chemical equation. I've gone ahead and balanced that for you. Let's talk about what we know. We know that before the reaction starts, I'm going to have some mass of hydrogen peroxide, but before the reaction starts, there's no product. We all know exactly how much we need, so we're going to be using up all of it. After the reaction, there'll be no hydrogen peroxide left, and I'll be producing some amount of water times that coefficient times the mole ratio. Okay, so let's figure out how many moles this is. They said that we want to get 0.77 grams of water. We need to convert grams of waters to moles of water to get our final answer right here. So you go to the periodic table, you find H2O, so hydrogen plus 2 oxygen, and you're going to get 18.02 grams. So take 0.77 grams of water, divide by its molar mass, and that'll give us our moles of water. So 0.77 divide by 18.02, and that's going to give us 0.0427. 0.0427. So that's how many moles of water were produced. Now, if we started with none and we ended up with this many, how many were made during the change? That same number. And that same number is equal to question mark times 2 over 2. I bet you can get this one without doing any algebra. What's 2 over 2? 1. So what times 1 is that number? It's that same exact number. So how much of the hydrogen peroxide must I have started out with? I must have started out with 0.427. I used up exactly 0.427, and there's none left over. Okay, have I finished the problem yet? No, because they want to know the mass of hydrogen peroxide. I'm running out of space right here. I'm going to try and kind of squeeze this in over on the side. Let's see, room over here. I'm going to squeeze it in right here. So 0.427 moles of hydrogen peroxide over 1. And every 1 mole is how many grams? I'll go to your periodic table. H2O2, there's 2 hydrogens and 2 oxygens, 34.02 grams per mole. 34.02. So 34.02. So let's take our calculator. We still have that same value in there. Times 34.02. That's going to give us 1.453. And that's going to be grams of hydrogen peroxide. Now, if you look back at the original problem, there's 2 sig figs. So this is going to be about 1.5 grams of H2O2. That right there is our final answer. Sorry, got a little bit cramped, but this is where your final answer is for that problem. Okay, one more problem on this page. We need to determine the mass of sodium nitrate produced when 0.73 grams of nickel 2 nitrate reacts with sodium hydroxide. We're going to say excess, or there's going to be at least enough of sodium hydroxide, according to the following equation. There is a typo right here. Make sure, we know that this is nickel 2 nitrate, so if you go back to our naming rules, nickel 2 is a 2 plus, nitrate you've memorized is a 1 minus. Do your crisscross, the formula should be NiNO3 2, okay? So make sure you put the little 2 outside. Okay, so here's our equation. It's already been balanced for you. They're giving you grams though. Remember, for our BCA table, let's set up what we know before we start. We know that before the reaction starts, I have some number of the nickel 2 nitrate. I'm assuming excess or enough of the other reactant. There's no products before I start. I'm going to use up the reactants during the change, completely using up the nickel 2 nitrate, and there'll be enough or leftover of the other reactant. And then they're asking me to try and convert the moles of the sodium nitrate into grams. So let's see, the first thing, we've got to get moles to put into our BCA table. So nickel 2 nitrate, let's go to our periodic table. Ah, look at this great periodic table. Nickel 2 nitrate's already right here, so it's 1 times nickel's mass plus 2 nitrates. Now nitrate is nitrogen plus 3 oxygen. Make sure you distribute through 182.71 grams per mole. So 182.71. So this is how I'm going to figure out my moles of nickel 2 nitrate. So let's take 0.73, divide by 182.71, and we're going to get 0.003995. So 2 zeros, 3995. And that's going to be my moles. So this is what number goes in right here. So 0.003995. And I'm going to exactly use up all of it during the reaction. So minus 0.003995. And they really are only asking about the sodium nitrate. So how much sodium nitrate, how much sodium nitrate am I going to be producing? I'm just going to move this over a little bit so I've got some more room. I'm going to be producing that 0.003995 times the ratio of the unknown sodium nitrate to the known nickel 2 nitrate. So remember, this is where I pull those mole ratios from. This is my recipe. That's where these numbers right here come from. So what are we doing? Essentially, we're doubling it. So times 2. How many moles did I make? 0.00799. Okay, so 0.00799. Yep. And then we need to figure out, so 0.00799, we need to figure out how many grams that actually is, because they don't want to know moles, they want to know grams. So the mass of sodium nitrate. Let's go back to our handy dandy periodic table of science, and oh look, sodium nitrate's already there too. 1 times sodium's mass, which you can find, up there is 22.99, plus 1 times nitrogen's mass, plus 3 times oxygen, gives us 85 exactly grams per mole. So this is going to be 85.00 grams per mole. So take that number in your calculator, times 85, and we're going to get 0.67921. 0.67921. 0.921. Last part is look for sig figs. There's only 2 sig figs in the original problem, so let's round that. This will actually be 0.68 grams of my sodium nitrate. Okay, that's about 15 minutes right now. I think I'm going to pause this video and I'm going to upload a separate video for the next page. See you next time. Don't wait to be great.